Do you want to use your own data in AI? Then look no further. In this video, we'll be talking about how to incorporate a RAG technique in AI agents. Let's get started. So first we are installing all the libraries that are not automatically inbuilt in Google Colab. So Pydantic AI, which will be used to create the AI agents, and PyMU PDF, which will be used to read the PDF data. Then we are importing all the required libraries. So from Google Colab, we are importing user data, which will be used to read the API keys from Google Colab. From Pydantic AI, we are importing all the Google providers so we can use the API key to connect to Gemini LLM. Then OS, we are importing to fetch the API keys from Colab and to store it in the Python environment. Requests and fetch libraries are used to fetch external sources like a PDF, and then fetch is used to work with them, like to extract data or just creating a new PDF or reading all the contents of the PDF. Then NumPy is used for the working with different numbered array. You will see later, like we have to work with the textual data to convert it to numerical, and then we have to work with the numerical arrays. So that's where NumPy comes in. And from Google Generative AI, we are importing Gen AI. From this, like we will be importing a module which will be used to create embeddings, which we'll see later. Then this is the same function that we used earlier, nbprint. This is just to print our outputs in a more intuitive way. So first step is to set up our Gemini model, which we are doing for the past 2-3 videos in this series. You can watch it again if you want. I will just skim through quickly. First, we are getting the Gemini API keys from the Google Colab, and we are importing them in our Python environment. And the Gemini model which we'll be using is the 2.5 Flash Lite. Then we are configuring the Gen AI also using the same Gemini API key that we have. Here we are importing the Google providers so we can connect to the Gemini LLM. Here we are giving our Gemini key and the model that we want. Then we are building a simple agent. We are calling it a RAG agent right now. So RAG agent will help us to answer the queries basis our context. So we'll cover in detail below, but this is just a simple agent RAG. We are giving the instructions that you are a RAG assistant. Use only the context to answer clearly. Context means just your own data. Like you don't want the LLM to answer just basis its training data. You want to provide some more data to it, which you know like it will not have access to. So let's say I just ran this AI agent. I just gave the query that, let's say, world ended in 2012 and now it's 2025. How many years have passed? So now you see, first I've given some information to it, and now I want the LLM to answer the question basis the information I gave. So I will just run this cell, run all of these cells, like importing libraries, defining our nbprint, importing the Gemini API key, and then running this agent. Yeah, so now you see the world ended. The current year is this. Therefore, 2025 minus 2012 is 13 years have been passed since the world ended. So it took that context, then it thought of its own, like how to get the required response. So it just checked, like the world ended in 2012, current year is 2025, then it calculated the difference. So now you see like how it is using our own data. So RAG is the same technique. Its full form is Retrieval-Augmented Generation. So we basis our query, we first retrieve the relevant context from the provided documents. Then augmentation means it will augment the context in your prompt. So whatever question you give, it will augment the context along with it. Let's say the context that we gave was this, and the question we gave was this. So it will augment both of these, and then it will generate the response. So Retrieval-Augmented Generation. So first of all, to retrieve any information, we first need to pass some information to the AI beforehand. So for this use case, simple iceberg index, this is just recently uploaded by MIT. This is just an index to measure workspace exposure across the AI economy. So basically it is just checking like how AI helps us in the workforce to interact with humans and to increase our efficiency. So here, this whole paper explains all the processes. Like I don't want to read it whole to you because we will be using the AI to summarize this project. So this you see is recently uploaded 29th October. You can get the PDF from here, which will have the whole paper, but we are not going to view the whole PDF. We are just going to copy the URL, and then we will be importing this PDF in our Google Colab. So the AI agent can give responses basis this document. As this is recently uploaded, so the trained LLMs will not have access to this data. That's why we have to provide the document to the LLM. So the first step will be to store the data that we have in a format such that the LLM can understand it. So like LLM is again like a computer, it will only understand numerical kind of data. So we have to convert the document into some numerical format. And then this is a long document, so first we need to chunk it also. We just call it, like, if you want to break it in some parts, we call it chunking. So we have to follow all the steps so the LLM can automatically get what is the relevant part of the document for the user query. So these are the steps that we'll be following. First, we'll be downloading the PDF from the link that I just copied. Then we'll be extracting the text from that PDF. Then we'll be chunking the text. So chunking, just breaking text into smaller pieces. Then we'll generate embeddings. So what are embeddings? Embedding, you can just imagine like we are converting the text to a numerical array. Array is just a list. So just imagine a text, and now that text is converted to a let's say 784 numbered list. So that list is like a vector in space. So when we have another user query, this user query also will convert into a text, and then we will compare different vectors that we have. Whichever vector is closer to the user query, that vector we will extract, and from that vector we will extract that part of document. So I have some simple image also, like this cosine similarity what we will be using. So let's say we have this orange, which is represented by this vector, apple represented by this p vector. When we want to check the similarity between, so let's say this A is our user query and B is some part of document. Both are converted to numerical format. So when we want to check the similarity between these two, we'll be using this formula A dot B by mod A mod B. This is like vector algebra. You can explore it more if you don't know, but this is what we use to check similarity between two vectors. So that's what we'll be doing. We'll be generating the embedding. Embedding is just the vectors from the text format. So the chunks will be representing as vectors. Then we'll prepare the vector store. We will store all the embeddings for different parts of document in a database, you can say, that the LLM can access. So the first part will be fetching the PDF, like getting the PDF into our Google Colab. So here I've just pasted the same URL that I copied from the archive site. Then this request library helps us from a URL to download a file. So I just need to say request.get URL dot content will give me the content of that file in this PDF bytes variable. Then we are saving this contents in a temporary PDF, so we don't have to download it again and again. So for that, like I'm just opening a temporary PDF. This is a new file I'm creating, and I'm writing our PDF bytes into this file. And then using the fits library, I'm opening my temporary file. So fits library is helpful to work with the PDF documents. So the full text, I'm just making an empty string. And then in this doc variable, the fits library will automatically separate the PDF pages to different list of pages. So I can iterate over it. So let's say I have 5 pages, then in a list, I will get the 5 pages. So I'm just iterating over the doc, like for page in doc, page.getText. This will get the text from that page. And then we are adding that text into our full text. So when it will be iterating, so from each page, it will extract the text form and it will add it in our full text string. And then we are also adding a new line character. So new line is just an empty line I'm adding after each page. So finally, I will just run this so you will see yourself what is the full text. Again, we are using nbprint to get some pretty output. And I'm just checking the first 10 characters because as this is a long PDF, the output will be very long. So I'm just checking first 10. Let's say if we want first 100 also, we can just say. So the first 100 characters we have extracted. And you see like this is having that project iceberg and the title of the PDF. And then like some writers' names have also come in the first 100 characters. So now we have downloaded the PDF and we have the textual data of that PDF in this full text variable. Then we will be doing the chunking. So step we will be dividing the full text into different chunks so the LLM can understand like which chunk to fetch for a given user query. So in this, we are just defining a chunk text. So I'll be taking the full text as the first argument. Max characters means in a particular chunk, how many characters should be there. So you can play around with this. If you go too long, then the LLM can get confused, like in which part of that chunk is the answer. If you go it too short, then there will be too many chunks. Then also like AI will get time to find the relevant chunks. So this argument you can play around basis your own document sizes. Then overlap, you will see like how this overlap is used. So I'm making a list of chunks. I'm iterating over the length of text and I'm taking a jump of max characters. The third argument means this is the jump. So first I will be going from 0 to 1000, then 1000 to 2000. So this is the jump argument you can say. Then start is 0 to I minus overlap. So now you see, let's say you are at the second chunk. You want to get the 1000 to 2000 characters. But if you just separate out all of the chunks in different parts, let's say there is a continuous line and that gets divided into two different chunks. So we will lose the information because in one chunk there is some information, in another chunk there is the rest of the information. So we don't want that kind of thing to happen. So what we are doing is instead of just having the hard limits, so when we are going to cut 1000 to 2000, we'll be extending the range by whatever is the overlap parameter. So instead of going 1000 to 2000, I will take 950 to 2050. So in both of the chunks, there is some overlap. So the information is not lost. So the start is 0. This max is done because in the first chunk, if you just do 0 minus 50, it will go minus 50, which can lead to errors. So that's why we are going max 0. So if it is negative, then it will be automatically put as 0. Then and is the minimum of length of text. So similarly, it can go out of range also at the end. So we are saying like the upper limit is length of the text. Then for the end point, we are giving I plus max characters, which is the 1000. So I is if it is 1000, then 1000 to 2000 will be the range. Plus minus overlap also. Yeah. So here, yeah, I have to add the overlap also here. So the both of the limits are extended. So then I'm appending in my chunks list text start to end. And then I am returning the list of chunks. So now I'm calling this chunk text function with my full text that I had extracted above from the PDF. And the second parameter I'm giving, max character should be 1000. I can give or not give the third parameter. So if I do not give the third parameter, it will take the default value of 50. So if you want to change, you can add a third argument, overlap equal to let's say 100 or 150 or whatever according to your need. So we will run this cell and then we will see what are the number of chunks it created from the whole PDF. And then I am just printing the first chunk. So we see the length is 64. So it divided the whole PDF into 64 chunks. And the chunks 0, I'm just getting the first chunk. This is again like the title, the author names will be there, and some part of the first text of the PDF will be there in the first chunk. Okay, then so now we are going to convert the textual data in the chunks to numerical format so we can apply the cosine similarity. So for the converting the textual to numerical format, I'm using genai.embed content. With this function, we can get the embeddings for a particular content using some model which can convert textual data to numerical data. So here we are just using a text embedding model. You can change it according to your need, but this just works fine. Content, we are giving the text that we have, which will go as an input to this embed function, sorry. And then task type is retrieval document. So we just have a retrieval kind of document we can give so that it can know like what kind of task it has to perform. Then we are returning an NP array. So this is to help getting those cosine similarity formula. We have to use the NumPy library. So from that response, we are getting the embedding and we are saying the data type is float format. This is just a numerical data type. So the whole embeddings, I am just making another array because for each chunk there will be an embedding, and then we will, that embedding is also an array. And then for different chunks, you have more embeddings. So there is an array of array. So that's why there is NP array. And again, there is a list embed C for C in chunks. So for each chunk, just do the embedding and store it in a simple NumPy array. So now we have an array of array. So the whole array has like 64 elements, which will be 64 embedding arrays of all the chunks. Then I'm printing length of embeddings, and I'm also getting like for the first chunk, I'm getting the vector. Again, this vector could be very long, so I'm just printing first 5 numbers of the vector. So we got the 64 embeddings for all of our chunks. And for the first embedding, I'm just printing first 5 numbers. Okay, so now you see it has converted the textual data into numerical data. So the second part of our RAG pipeline will be user query answering. So now we have a vector data store. So for the content that we had, we converted it into chunks. For each chunk, now we have embeddings. So now we can say we have a vector data store from our content. This is the first part of RAG pipeline. Second part is how the user queries will be responded. So the steps will be again similar. For the user query, we will get the embeddings. For each of the embedding in the vector store that we have, we will check which embedding is closely representing to this user query. Then we will be selecting some top chunks which are most similar to user queries that can give us information for the user query. And all of these top 3 chunks, let's say, these we will give to the LLM as context. Same way that I gave the context, like the world ended in 2012. Same way we'll give now we will give the context as the chunks that we got from the document. So the user query will be input from the user. Embed query will just embed the user query as a vector embedding. We'll search the vector store for the most closely representing vectors for the user query. Then we will retrieve the chunks. Let's say top k chunks we can get, or k you can vary, top 3, top 5 chunks, whatever you need. And then we will generate the answer using LLM. So here I have just made some user queries. This is our first step, user queries. So what is iceberg index? What problem does it aim to solve? And many more questions that I could think of. And all of these you can ask from the LLM, but you need to provide the context. So now we'll see how we'll provide the context. So first step is retrieval. Retrieval just means like retrieving the relevant part of context from the whole vector store for our user query. So in the retrieve context, the user question will be taken as an input, and how many top chunks we are going to fetch, that will also be a parameter. This again, you can vary, like if you want to give more context to the LLM, then you can increase this parameter, but it can also confuse the LLM. So again, this is you have to play with. So this is the embedding for the question. We are just using the same embed function that we had defined above, but giving the question as an input now. This is the similarities that I had shown in this similarity of A comma B. This you see is A dot B by mod A mod B. This is norm A norm B also called. So now we are getting embeds dot dot. This is the same dot product between the embeddings and the query that we have, and dividing by the norm of embeddings and norm of the question. So all of these we got the similarities, like for all of the chunks that we had, we got a similarity score, you can say, for our user query. So all of these scores we will be sorting in decreasing orders. We know like which are the top most important chunks. So for these, again, I'm using NumPy library dot arcsort. Arcsort means sorting the whole array and then getting the indexes which are most important. Because we don't want the numerical embeddings, we want the textual output in the end. So I'm just getting the indexes of those embeddings which are the most closer. Using those index, I will get the actual textual data from our chunks. So I'm just sorting it the sims array. I'm sorting in the reverse order. This is used to reverse NumPy array. Now we got the indexes because we are using the arc sort. We have just taken the top k indexes. So here again, I have to give this indexes is sorted sims index, the top k. So this is slicing the NumPy array for the top k elements. And then I'm joining all the chunks in this indexes. So I'm just fetching those chunks with the indexes which are having the most similarity with the user query. So I'm iterating over all the indexes in this IDXs list, and then I'm giving it to the chunks list so we can get the relevant chunks. And finally, I'm joining in it a single string with just two new line characters between each of the relevant chunks. So I will get the output also that you can see like how this is all performing. The second step will be augmentation. Like I said, first I will get the context, and that context I will feed it as a prompt to the LLM. So for the context, I am using the retrieve context function that I had used, giving the user query. Top k I am giving as 3, so I need the top 3 important chunks from our vector store. So this verbose function I'm just using. So if you want to see the actual context, you can use this verbose function. This is just used to get more output, so you know the inner functionality also. So I'm just giving verbose default value as false. If you give it as true, it will print a straight line first, then it will print the context and again straight line. So you know like what is the context and then what are the responses. So now here I'm using the augmentation. So context I'm providing new line. This is again new line character. This is the context that we will have. Then again two new line characters, the question that the user has, and then I'm just saying like answer only based on the context. Then I'm returning the augmented prompt. So this augmented prompt we will give it to the LLM so that it can respond. Then I'm again defining a function. This is async because again, like when we run a AI agent, we can use async parameters. So whenever we execute some queries, let's say you want to give 10 queries. So it does not wait for one query, then second to third, fourth. It does not run in sequence, but in parallel format. So the async is like running in asynchronous manner. So it does not stops the execution. It will just pause the execution there, and then it will run the remaining parts as well. So if we give 10 queries, it will run the first one, then second one, third one. It will not wait for the first one to finish up. It will keep running. And then whenever the results are coming, it will give the results back. So that's why async define is used here. Answer with agent is just function name. I'm giving a prompt. From our RAG agent that we defined, I'm just giving run with this prompt. Whatever is the response, I'm giving the output as the return of this function. So let's say I just took the first user query that I had defined above here. And the first step will be to augment this query with the context. So for this, I'm using the augment function. I'm giving the query. Verbose I'm given true, so I want to see all the outputs. So now you got the augmented prompt. Then I'm using this await keyword because I'm using an asynchronous function. So to get the output, I have to use the await function. So the execution, whenever it finishes, it will give the response back. Then I'm calling this function with the augmented prompt. And then I'm printing what is the question and two new line characters again. Then what is the answer, two new lines and the straight line. So when I run all of these, so let's say here user queries I will run. I will define the retrieval function, define the augment function, and define the answering with the agent function. So now I will run this. So yeah, here you see like this is the straight line that we had here, and we print straight. This will just print a straight line. Then these are the top 3 chunks that it extracted from the document. So this project iceberg, unemployment, whatever, all these paragraph, then second, then third, all these 3 contexts, then it used these 3 as the context to answer the user query. The user query was what is the iceberg index? And the answer is iceberg index is a skill centered measure of workspace. So all of this, like it has extracted from the document itself. So now you see how it is working. It will first convert the user query to a vector embedding. Then it will check in the vector data source which are the top most important vectors. And then basis those vectors, it will again get the text back from the chunks list. For the all three most important vectors, it got the text. These three texts, it will give it to the LLM as an augmented prompt. And then from that augmented prompt, the LLM can give us the answers. So let's say like we can make some another question. Yeah, what are the three main steps of Project Iceberg simulation process? So this is the fourth item, but the indexing starts from 0. So 0, 1, 2, 3. So I'll give the third user query. Then let's see the response. So yeah, here it's saying you human workforce mapping, AI workforce simulation. So yeah, here you can search this also. Let's see like if it in the document it is there or not. I'll just click on view PDF. Yeah, so here I will search human workforce mapping. Yeah, so here you see the step 1 is human workforce mapping, second is AI workforce mapping, and third is human AI simulation. So the same three it has given here also. So it has extracted the relevant context and then it has given the response back to us. So the same thing like you can try out with the different questions. Again, all of this code is available on GitHub. You can play around with it and give different user queries, try to change these parameters, try to see if we decrease the overlap, then also it is able to give. So let's just test it. Let's say if I decrease the overlap to 5, so there is no overlap, there is a chance like the information can be lost between chunks. So I'll just run these again. I will get the embeddings again. So the important thing about vector embeddings is also like it will just not convert to some random numbers. It will convert it such that two similar sounding or similar meaning sentences will have similar vectors. So their cosine similarity will be high. So whenever two different sentences have semantically similar meaning, it will have the vector embeddings also such that their cosine similarity is high. That's how like this is extracting the most important context for us. So this is run user queries again. These are all functions, so we don't need to run it again. Then let's say if we gave this again, AI workforce, human AI, and scenario. So here you see, because the information was lost in between different chunk, here you, let's see like in which chunk it is there. Here you see, in the third important chunk, the step 2 came. So this chunk was cut in such a way like the first step went in the earlier chunk, the second step went in the later chunk. So now it only saw AI workforce and human AI simulation. So it gave AI workforce and human AI simulation, but the first step, the human workforce mapping, this it could not find because the chunk was lost. And now it gave scenario testing as the third, but this is wrong. So you see now like how that overlap parameter itself can change the responses because we lost some information. If we increase that, then that is possible that step 1 would be included in this chunk and then the context would be there. So the LLM would be able to answer. But now the LLM is not able to answer because the information got lost. So that's why like according to your own use case, you have to change all of these parameters. You can use some more things also. Like this is just a simple chunking that we have done, like just dividing into 1000. But here also like there are many more techniques, many more optimizations. Like we will be covering all of these in some later videos. But this is just a simple rack pipeline that you can manually build and just test it on some documents of your own. So that's all that I had for this video. We'll be seeing again in the next video. We'll be covering LangChain and LangGraph, which are another most important libraries, just like Pydantic AI for AI agent development. So we'll be seeing you in the next video. Take care till then.